In this lecture, we will discuss about camera geometry. We have already discussed how a three-dimensional scene point is mapped to a two-dimensional image point. Here, as we know that if I consider a three-dimensional scene point P, then from there if I draw a straight line which passes through the center of lens and which intersects the image plane at another point some small p, that forms the corresponding image point. Now, logically we can consider also in the same way of image has been formed in the front of the camera, where the corresponding image plane is placed at the same distance, where usually the sensors were placed behind the lens. The distance between that plane of sensors, that distance if I keep it same, then you will get the images of the same size, and there is a logical transformation of coordinates from this point to this point that we can consider. So, this is a convenient way of representing the coordinate system, and we will use this principle while explaining the mapping of three-dimensional scene point to two-dimensional image point using this kind of projective geometry. So, let us consider the principle here, how these are related. So, this is the configuration what is usually shown for pinhole camera mapping, and here in the pinhole camera once again center of projection is taken as the point which connects from which all the rays are emanating and which is projected on the image plane. So, the point of intersection, that is the image of the corresponding three-dimensional points. So, only thing here that you should notice here, we are interested to know also the mapping of physical three-dimensional coordinates in the scene to the corresponding two-dimensional image point in the image plane. Though the ray, complete ray, it is represented by this point in the sense of projective geometry, but physically images are formed by the phenomena of reflection, from where energy of the reflected point, those are focused at this point. So, we are interested to build up that relationship, and mathematically if I know this point, then it is very easy to establish the relationship between the coordinates of the image point and also the coordinates of the three-dimensional point. Where now we have to consider some convenient representation of this coordinate system. So, let us consider the center of projection or the camera center as the origin of this coordinate system, and also the axis of the three-dimensional coordinate system. Those axes, the particular x axis and y axis of that three-dimensional coordinate system, that is parallel to the coordinate convention what is followed in the image plane. The origin of the image plane's coordinate, that is formed by the intersection of the z axis with that image plane, and this is considered as the origin of the image plane. And as I mentioned, this x and y axis, they are axis parallel with respect to the three-dimensional coordinate system. So, with this convention, then it is very easy to compute the coordinate x and y from the three-dimensional coordinate, which is represented here by upper cases of x y z or capital X y z. We can apply the law of similar triangle. We assume this plane is at a distance f, because f is the focal length of the camera. So, in that case, by applying this law of similar triangle, we can find out that so these are the points and this is the image coordinate, and as I mentioned, this is the focal length, and then these are the expressions that we get, that is the coordinate x is equal to the f x by z, and coordinate y, this coordinate y is equal to f y by z. So, you are using these coordinates of the scene point to get this computation. You can apply the law of similar triangles, because you can see that if I consider the triangle for finding out the x coordinate. So, this is the x from the yz plane, and so the corresponding x value at this point, and this is a similar triangle. So, that would be, so this length is f, and this length here in the coordinate system is called z. So, it is f x by z. Similarly, y is also considered as f y by z. So, this is how we map a 3-dimensional coordinate points to its corresponding 2-dimensional image point. You see that we are using actual scene coordinates for which this image has been formed. So, if I give you x, y, z, it is very easy to get this point x and y, but inverse is not true. If I give you the image point, naturally it is represented by the whole ray, and it is unless you specify some other constraint, you cannot say that it is image of which point. So, let us see how we can resolve all these things. And another thing I should mention, another nomenclature we will follow. We call the xy plane of the original 3-dimensional coordinate system is called the principal plane, and the z axis of that coordinate system is called principal axis. So, mathematically we have seen already, we have written in the form of an equation which is given by this x equals f x by z and y equals f y by z. And so, this equation can be represented by a matrix form if I use a homogeneous coordinate system of homogeneous coordinate system for representing the points. How we can do it? Let us see. So, this is the representation. As you can see that the coordinate point x, y, z, it becomes in the homogeneous coordinate system, you have an additional dimension. So, it is a 3-dimensional homogeneous coordinate system, and or you can say also this is a 3-dimensional projective space. That is why it is a point in the projective space P 3 or P q, that is how we can call it, and this point is mapped to a 2-dimensional image point, a point in the 2-dimensional projective space, which is given by this x y 1 is a scale factor. You can see that the trick here in this representation, since this f x and f y, if I divide it by z, then we get the actual image coordinates. So, this multiplication, matrix multiplication, will provide you this representation of f x, f y, z in the projective space, in a 2-dimensional projective space, which is equivalent to the image point. That is why this mapping can be expressed as a linear mapping in a in the projective space, and it is a mapping between a 3-dimensional projective space to a 2-dimensional projective space. So, that is the difference between homography, what we discussed in earlier lectures, where a homography was defined in our context as a mapping from a 2-dimensional projective space to another 2-dimensional projective space. That is one difference. Here it is from 3-dimensional projective space to a 2-dimensional projective space. The other difference was that a homography was invertible. So, mapping was unique 1 to 1, but in this case, as you know that a 3-dimensional point, though it is mapped to a unique image point, but it is not true for the image point when it is again projected back to the 3-dimensional space. Then it becomes a projected ray, and any point in that ray is represented by this image point. That is why this mapping is not invertible, and you can see also from the dimension of this matrix, it is not square matrix. That is one of the conditions where you should have an invertible transformation for a linear transformation. Of course, singularity, it should be non-singular also, but in any case, since it is 3 cross 4 matrix, so we can straight away we can say that this mapping is not an invertible mapping. So, this matrix is called projection matrix, and this matrix can be also represented in this form. You can see that it is a it is formed by multiplication of or composition of two matrices, where this is a 3 cross 3 matrix. So, this is a 3 cross 3 matrix and this is a 3 cross 4 matrix, and the corresponding the structure of the matrix, they are very simple, and you note the notation what we are using for representing this matrix, this particular matrix, which contains the information of the focal length, that is represented in this in a short form. We will be using this notation because it is a diagonal matrix. We will be simply listing its corresponding diagonal elements, whereas for representing the other part of this the right hand side matrix in this component. So, there are two submatrices. One submatrix is an identity matrix. So, this is a 3 cross 3 identity matrix, which is shown here in this form I, and the other submatrix is a column vector, which is a 0 column vector, which is also shown here in this representation. So, this is a short form of representation of a projection matrix. There are motivations for representing in this form that would be clear when we perform the corresponding different mathematical operations on these matrices. So, let us proceed and we will understand the why we are taking this kind of representations. So, we will try to generalize this coordinate mapping considering different other scenarios. So, in the canonical form, as we discussed earlier, we have considered the projection plane or the image plane, the axes in the image plane, they should be parallel to the axes what are used for the 3-dimensional coordinate system. So, there are two coordinate systems in this configuration. One coordinate system is the 3-dimensional coordinate system, which is also called world coordinate system. The other coordinate system, which is called image coordinate system. So, this image coordinate system also has its own coordinate convention, and that is the representation of the corresponding 2-dimensional image plane, and you can also consider that is represented by a 2-dimensional projective space. So, it has its origin here, and in this convention in the 2-dimensional real 2-dimensional space. So, it has its origin, and this origin is formed, as I mentioned, as an intersection of the optical axis or principal axis, which is the z axis, with the image plane. So, that is how this origin is formed, and then axes are parallel, I told you. So, this is the canonical configuration, and in this case we are assuming, of course, this image plane is at a distance of focal length f. In the further canonical form, even we can normalize it at a distance 1. We will discuss in the previous representation itself. We have seen that we have taken out the focal length outside of the projection matrix, and the other right hand side component, which contains only identity matrix and the 0 column vector. So, if I use only that projection matrix representation, then that is the minimal representation of this minimal configuration of this imaging, where projection plane is also taken as a unit distance from the center of projection. So, but let us consider we can have a different coordinate system in the image plane. We have origin, we can have origin at different positions, say. So, in the canonical form, what I discussed here, when the image plane is at a distance of f from the principal plane, then we considered that x and y mapping of a 3-dimensional point capital X, Y, Z to a image point small x, y are shown by this equation. So, that we have discussed already. These are the two equations. Now, so when we consider a coordinate axis, when it is a different coordinate system, that means origin may be shifted at some other point, but we may consider our principal, our coordinate axis, they still remain parallel to x axis and y axis. So, when the origin has been shifted to a different point, so the principal point will have a coordinate which is other than 0 0 of the image plane. Suppose this is Px and Py. So, any point in the image plane, say any point in the image plane, it will be now represented as its coordinates will be then Px plus x and Py plus y. So, in this case, what we can get, the new coordinates, this coordinate can be if I consider this is the new coordinate system, say this is x prime, y prime under this transformation of the origin or translation of the origin, then x prime can be written as Px plus f x by z and y prime is Py plus f y by z. So, this is how these expressions, these coordinates should be interpreted, and in the matrix form, if I transfer this relation, then we can write this relation simply in this form. That means, the projection matrix, as you can see, the third column of the projection matrix will have will be changed from 0 0 1 to Px Py 1. You can verify the corresponding expressions. You will see that the x prime is equal to f x. So, this operation will give you f x plus Px. So, if I simplify this matrix multiplication, we will find out this operation will give me f x plus Px, then f y plus Py, then z, then z, right. So, this is a two dimensional projective space, point of the two dimensional projective space, and z is a scale factor. So, finally, x prime can be represented as, so sorry, this is Px z and Py z. So, when I divide this by z, it would be Px plus Fx by z, and similarly for y coordinate Py plus Fy by z. So, this is equivalent to this coordinate system. So, this is how the shift of the origin in the image plane affects the projection matrix. So, this is the form of the projection matrix when there is an offset in the origin of the image plane, and this offset is given by Px Py, and which forms the third column of this projection matrix, so this particular information is contained in the third column of the projection matrix. So, once again you can decompose this matrix into the form what I discussed earlier. You can see that this part remains the same, that is the canonical form of projection matrix when your image plane is at a distance of unity in front of the camera center. So, this mapping is very simple, it is an identity matrix, and this column is the 0 vector column, and once again this is represented by this particular matrix, and K is representing this 3 cross 3 matrix. So, this 3 cross 3 matrix is represented by the symbol K here, which is called incidentally calibration matrix. We can see that this is camera calibration matrix, and you can find out in this matrix we have some of the parameters which are defining the image coordinate convention, mapping from the 3-dimensional mapping of the image coordinates, canonical form of image coordinate to its corresponding coordinate what has been observed in our what is given to us. So, what are the elements there? You can see that once again the diagonal elements, particularly it is formed by the corresponding focal length, that is diagonal f1 that is there, and these are the offset principle. So, finally, the relationship between the image point and the three dimensional scene point, that can be summarized in this form as this is the image point, small, it is represented by this convention. I will be using the small letter to denote any image point, and sometimes I will be using the bold font just to denote that it is a column vector. Similarly, the upper cases, they are the world coordinate system, and they are all represented in homogeneous coordinate system. Now, let us consider that your world coordinate system also is different from the camera centric coordinate system. That means, your origin of the world coordinate system is different, and also the axis of the world coordinate system, they are at different orientations, which are not parallel to the axis of image plane. So, this is the canonical configuration what we discussed earlier. So, this is the canonical form we discussed. So, this is the canonical form, but this is the actual coordinate system, world coordinate system, what we will be considering. So, that first we need to consider the transformation between this coordinate system and that and the corresponding canonical coordinate system. So, there is a there are operations like rotations of axis and translation of origin, those are involved in transforming any coordinate to the corresponding canonical world coordinate, canonical camera centric coordinate system. So, this could be related by this could be related by this simple form, where R is given by a rotation matrix, which is a 3 cross 3 rotation matrix. So, first you have to shift the coordinates of the three dimensional point. Incidentally, you note that there are two type of representation of coordinate representations in our discussion. One is that representation in the non-homogeneous coordinate space or inhomogeneous coordinate space. So, that is the normal three dimensional coordinates what we use in our analytical geometries, and the other representation of the same coordinate point in a three dimensional projective space, or we call it homogeneous coordinate system. So, in this case these relations, it involves only the coordinates in the usual convention of non-homogeneous coordinate system. Even the center is also represented. So, the symbol tilde, when I will be using symbol tilde over the point symbol of that point, then I will consider the coordinate representation is a non-homogeneous coordinate representation. Otherwise, if this symbol, this tilde is not there at the top of that symbol, then usually unless I mention, that is represented in homogeneous coordinate system. So, you can see that the first you have to translate the point by its translate the point from the camera center. So, translate the origin by this operation. So, this is the corresponding location of the center. So, first you translate the point to this center, and then you apply the corresponding rotation at this point, and then you will get the corresponding transformed camera coordinate system as in the camera coordinate system. So, this is the transformation which is well explained by any analytical geometry book. You can refer to it. So, R is in the structure of, it is a 3 cross 3 matrix which is called rotation matrix, and any coordinate x prime, it can be expressed in the coordinate system, camera centric coordinate system by this particular operation. So, now what we need to do? We need to apply this transformation of x to this canonical coordinates, camera centric coordinate system, and then we can apply the same projection matrix. So, which can be expressed in this form. So, you can see that in this expression, I can express this transformation of a coordinate system in the world coordinate to a camera centric coordinate system. All are expressed in the form of a 3 dimensional or homogeneous coordinate part. You notice that this is the x tilde part, that is the homogeneous non-homogeneous coordinate representation. If I add another additional dimension, then it becomes homogeneous representation. And this operation, so this r x tilde and minus r c tilde, which is explained by the submatrix multiplication. So, I can write this multiplication, I can also express this matrix in this form 0 1, and this is x tilde 1, where x tilde is given by x y z. We can apply the relationship with the projection matrix with the camera centric system. So, you know already that when your coordinate convention is the camera centric coordinate convention, that is the canonical form once again we discussed while deriving projection matrix. The relationship between the image point and the corresponding coordinate in the camera centric coordinate system is given by this. So, once again this K is the camera calibration matrix, which is a 3 cross 3 matrix, and I is an identity matrix, and 0 is the corresponding column vector. And this can be further expanded. So, this x c again can be related with the 3-dimensional coordinate system, which is observed 3-dimensional coordinate system in this form. So, finally, this is a mapping of point. So, there is some problem here, it should be x, okay? It should be this point. So, finally, you see that the whole expression, this part, it provides you a corresponding cascade of matrices, and if I multiply all these matrices, this is a matrix which will be of dimension 3 cross 4, because K is of dimension 3 cross 3, this is of dimension 3 cross 4, and this is of dimension 4 cross 4. So, if I perform matrix multiplication, and this matrix we represent by this a symbol P, which is called projection matrix. So, this projection matrix of 3 cross 4. So, if I multiply once again this projection matrix with the 3-dimensional coordinates in the projective space of a scene point, then I will get its corresponding image point once again in a 2-dimensional projective space. So, that is how we derive the relationship in a more general case. So, to summarize this representation once again in a brief form, we are showing here. So, as I mentioned, so this matrix is considered, this is as the projection matrix, which is shown here in the symbol P, and it had, and the whole composition can be shown in different way. Suppose I am taking out the rotation matrix out of this operation. So, I can also equivalently represent this matrix as K r into I minus C tilde. So, in this case you see K r, this is a 3 cross 3 matrix, because K is a 3 cross 3 matrix and R is also a 3 cross 3 matrix. So, it is a 3 cross 3 matrix, and once again this is the identity matrix, and here instead of a 0 column vector of this form, what we get here? We get negative of the coordinates of the camera center. That is very interesting. So, we can from the projection matrix elements itself, we can determine the position of the camera center in the world coordinate system. There we will come to that part in my next slides, how that computations will be elaborated. The other form of representations, once again you see that if I only take K out of this box and put R inside this part 3 cross 4 matrix, then it has two components. One is the rotation matrix and the other one is the translation. So, this gives you the corresponding coordinate transformation parameters of the world coordinate to the camera centric coordinate system. That means, you can get the rotation matrix, you can get the translation of the coordinate system, translation of the origins. If I can if I can find out what is the matrix K. So, from there we can get all these components. So, these forms are interesting because this can give you different information from the projection matrix itself. So, when we observe a digital image, actually we observe the pixel coordinates, and how a pixel is defined? A pixel is defined by an element, by a sensor, and which is usually a CCD sensor for a digital camera. It could be also CMOS sensor. There are different sensors, but each pixel is information of each pixel is captured by a sensor. So, we usually call this arrangement of pixels as a CCD camera arrangement. So, in the CCD camera arrangement, if I consider that configuration, then we need to also consider the parameters involved in digitization of the points in that corresponding sensor plane. So, there is a resolution involved there. So, let us see that we have already shown that how a projection matrix is component of projection matrix we have shown without considering the parameters of a CCD camera. But let us consider that per unit length there are mx number of sensors. So, mx is the sensors number of sensors in the horizontal directions, and my is the number of sensors in the vertical directions. So, this is how a unit length has been covered by that many number of sensors. So, if I consider a length f in the calibration matrix, so because this is f is a multiplication factor of that length. So, in our case we will consider the f can be replaced by this transformation as alpha x, which is f into mx, and alpha y, which is f into my in their respective places. So, which means that our camera calibration matrix, when we are considering this number of pixels per unit length along x and y axis, then it will look like this. So, it is alpha x, alpha y. So, these are the diagonal elements. Instead of f, we have now alpha x and alpha y, which takes care of the resolutions of the pixel resolutions of the camera. And then there is also another issue, that the alignment of the sensors in the horizontal direction and vertical directions may not be always rectilinear. There would be small deviations because of the manufacturing, very small though, still that can be that should be accounted for. So, let us consider that instead of the angle it forms 90 degree, there is a small deviation. So, it forms a angle theta from this perpendicular direction. So, this is providing a kind of a skewed coordinate system. So, we need to take care of that, we need to correct that skew, and this is taken care of by introducing another parameter into the calibration matrix, which is shown here, which is given by S, and which is actually which can be derived from the corresponding coordinate transformation. You can also verify that it would be tan theta, or even you can say sin theta. Theta is very small. So, you can write it as S equal to theta also in the radian in the radian unit. So, this is the final form of the calibration matrix, and then we in a general projective camera matrix can be described when I consider all sorts of parameters, all sorts of transformation in this form, that it consists of the elements. These are the corresponding elements, like k is now it has 5 elements like alpha x, alpha y, s, p x, p y, and also the other component which is which contains the other parameters, rotation and translation. So, these parameters they are grouped into different forms. So, there are 11 degrees of freedom in this particular projection matrix, because you know that it is associated with a scale factor, and so there are 12 elements. So, considering the scale factor, so there are 11 parameters, and there are 11 independent parameters. So, 3 of them will denote a rotation matrix, which is rotations along 3 axes. Then 3 will denote the translations of a 3-dimensional coordinate of the origin to the camera center, and 5 is 5 parameters are related to the calibration matrix, which are given by these elements alpha x, alpha y, s, p x and p y. So, in total there are 11 independent parameters, and out of them the extrinsic parameters, which are related to the transformation of world coordinate to the camera centric coordinate system, those are given by this matrix, that is the right side matrix of 3 cross 4 matrix, and the intrinsic parameters are inside the camera calibration matrix. So, these 5 parameters are called intrinsic parameters. So, with this let me stop here, and we will continue our discussion in the next lecture. Thank you for your listening.